Hi everyone, my name is Jerome Bellegarda and I'm Distinguished Scientist at ETSI. In this video, I'd like to give a brief overview of a paper entitled Pareto Efficiency of Learning for Getting Trade-off in Neural Language Model Adaptation, presented at ASRU 2023. This is work done at Apple before joining ETSI, where we looked into the retention of domain-independent pre-training knowledge while fine-tuning for downstream tasks. I'd like to acknowledge the contributions of my former colleague Wanhui Chen, who was an intern at Apple from National Taiwan University. Given that pre-training a language model involves a huge amount of data from a large variety of sources, the resulting LM is typically very good at capturing generic language usage. Obviously, it is desirable to retain this useful world knowledge when fine-tuning for downstream tasks. But it turns out it's not so easy to do because of the pesky trade-off between learning and forgetting in language model adaptation. In this work, we aim to better characterize this trade-off from three complementary angles. First, we make a distinction between data level and distribution level adaptation. Then we leverage an adversarial framework to regularize the adaptation process. And finally, we adopt Pareto efficiency as a key performance indicator. So let's get started. As a concrete case study, we consider the adaptation of a language model to an individual user's personal style. And we set up an adaptation framework where domain differences are a proxy for user differences. Specifically, we pre-train a neural LM on Wikipedia-style formal data and adapt it on conversational-style informal data. So adaptation from formal to informal domain is a proxy for adaptation from generic to user domain. We use varying amounts of adaptation data to simulate multiple user types, and as evaluation metric, we measure perplexity on two different test sets, formal and informal, which means that ideally we'd like to achieve low perplexity on both test sets simultaneously. The typical way to approach this problem is through fine-tuning. During pre-training, generic data is used to train a language model which encapsulates the pre-trained distribution, let's call it Y. Adaptation data is then used to fine-tune this model in a classical transfer learning approach, leading to the adapted distribution Y hat. This is typically done using the cross-entropy loss for next token prediction, which is defined here. But careful, in this formula, nothing prevents Y hat from drifting away from Y. To address this shortcoming, we perform distribution level adaptation on top of data level adaptation. This is done through the GAN framework that is shown here, where the discriminator evaluates how different the adapted distribution is from the pre-trained distribution. The idea is that the generator of the GAN should of course adapt to the user data, but also at the same time retain close alignment with the pre-trained distribution. In this setup, we minimize the usual GAN adversarial loss in addition to the previous cross-entropy loss. So the overall objective function can be thought of as a mix of the two losses with the balance between the two controlled by some weight lambda. In essence, the adversarial framework serves to regularize the adaptation process. And once the GAN has converged, the generator constitutes the desired adapted LM, and the discriminator, in effect, has performed local divergence minimization. To visualize the learning forgetting trade-off, we report results on a 2D plot that looks like this, where the x-axis represents perplexity obtained on the generic test set, and the y-axis represents perplexity obtained on the user test set. The upper left corner of the plot is the region of formal domain, and the bottom right corner is the region of informal domain. As we move downward vertically, more learning takes place, and as we move rightward horizontally, more forgetting takes place. This plot is a good way to visualize not only how close we can get to the ideal behavior in the lower left corner, but also how to characterize the trade-off between learning and forgetting. We can imagine that different Pareto fronts would represent different best possible trade-offs between those two objectives, depicted here by the hypothetical dashed gray lines. Increased Pareto efficiency would then be tied to steeper Pareto fronts. So let's see what actually happened with the setup described earlier. As expected, the pre-trained LM here in red is quite good on the generic test set, but not so good on the user test set, while with the LM trained from scratch here in gray, it's exactly the opposite. No surprise here. The interesting thing is where fine-tuning will land. With a large amount of adaptation data, we see that in the course of adapting to the new domain, the model has learned quite a bit about the new domain, basically as much as the LM trained from scratch. That's the good news. The bad news is that it has also forgotten a lot about the old domain. And with a small amount of adaptation data, we see a much smaller departure from the pre-trained LM, but then in terms of learning, the outcome stays quite far from the model trained from scratch. So basically, more data leads to more learning and less data leads to less forgetting, and the exact trade-off depends on the amount of data available. The associated empirical Pareto front can be visualized as shown here. Any point on that front is Pareto efficient in the sense that the solution cannot be improved upon without sacrificing something else. The question is, can we tweak things so that we can jump to another front maybe? To dig a little further, let's define an empirical zone, here in yellow, where we'd like the model to operate. Then we see that fine-tuning in this example with a small amount of data is okay, but with a large amount of data, we need to apply mitigation strategies to make the model forget less. And one of these strategies, of course, is early stopping. And indeed, we see that if we stop transfer learning at the correct time, we can find solution within a yellow box. But of course, knowing when to stop is tough, as becomes painfully apparent with a small amount of adaptation data. Indeed, in that case, we see that the best fine-tuning compromise now requires training to convergence. So, early stopping is tricky to get right. Now, another mitigation strategy to make the model forget less is to play with a mix of adaptation data itself. Before we dig into that, let's first zoom in onto the yellow operational zone so we can get a closer look. Here are the same points as before, all lying on or very close to the same Pareto front. Now let's change the mix of adaptation data to include half generic and half user data, which is potentially the case when looking at data not just generated, but more generally accessed by the user. We see that once again, the point lies on the same Pareto front. So clearly, we're not going to make any further progress with data level adaptation only. Hence the idea of imposing distribution level constraints through adversarial adaptation. Now let's look at the results with the proposed adapt framework. Whether the amount of adaptation data is large or small, adversarial adaptation achieves slightly better learning than fine-tuning with substantially less forgetting. This leads to a much steeper Pareto front, here depicted by the dashed green line. In addition, the gap between the two fronts, let's call it the adversarial gap, steadily widens with more adaptation data. We conclude that applying distribution level constraints on top of classical fine-tuning becomes increasingly advantageous as more adaptation data becomes available. To wrap things up, let's take a look at the kind of language usage typical of the different models. For that, we run in generative mode, given a particular sentence start. Here, the sentence start is the pretty generic this, and we observe completions in red with the pre-trained LM, in green with adversarial adaptation, and in blue with classical fine-tuning. We can see clear style differences between the three versions. Not surprisingly, the pre-trained LM is the most formal and the fine-tuned LM is the most informal, with adversarial adaptation falling somewhere in the middle. If we now use a more clearly informal sentence start, the trend is confirmed. The pre-trained LM's generation focuses on dates and times, which are related to formal information. In contrast, the other two versions are more conversational, and we see that given an informal context, adversarial adaptation has moved closer to informal completion. This shows that adversarial adaptation has properly captured the user domain. So to summarize the key takeaways, first of all, relying on data level adaptation is tricky to get right, so imposing distribution level constraints can help a lot. The proposed adversarial LM adaptation framework offers a better compromise between learning and forgetting through regularization and leads to a more productive use of all the adaptation data available. And finally, thinking in terms of Pareto efficiency is beneficial for a more holistic assessment of adaptation effectiveness. Okay, so we've come to the end of this presentation. If you have any question on any aspect of the paper, feel free to drop me an email at the address shown here. And thanks very much for watching. Bye-bye.